Okay, so here's our list that we have found, and here's my coffee. All right, so we found these powers. 2, 2, 6, sorry, these sums. 2, 2, 6, 14, 34, 82, 198.
They don't seem to have a lot in common.
They don't seem to have a lot in common.
Well, they're all even.
Ooh, okay, good observation.
And they get big pretty fast.
They do get big pretty fast.
Well, I see something.
Oh, I'm actually really interested to see what patterns you guys see here.
Well, for the first ones, it's 2 plus 2, and then you add another 2.
Okay. So 2 plus 2, then add another 2, you get to 6.
But the pattern doesn't continue.
Yeah, but if you double 6, you add 2, you get to 14.
If I double 6 and add 2, I get to 14. Okay.
Well,
But doubling 14, well, that gets you to 28. The pattern won't hold up.
but if you continue it with if you add 6 to it,
Add 6 to what?
add 6, so you multiply it by 2, add the previous number.
High 5. Double 14, add 6,
34.
34. So what does the pattern continue?
It's,
So
What happens when you double 34?
then you add 14, and
Well, double 34 you get,
you get 68,
and you add
82.
82. So it seems like to go from the previous two numbers to the next number, you take twice the previous number and add the one that was 2 back. 2 times 2 is 4, plus 2 is 6. 2 times 6 is 12, plus 2 is 14. 2 times 14 is 28,
plus
6 is 34.
Keep doing
2
it.
times 34 is 68 plus 14. So it looks like we have a pattern that says, I don't know what to call this, P of n. For any number n, I take the one right before it. Sorry, it's probably hard to see. Where can I write this? I'll write it down the column. Pn equals 2 times Pn minus 1 plus P sub n minus 2. That's what it looks like to me.
Oh.
I take this one is twice the previous one plus the one that was 2 back. This one is twice the previous one plus the one that was 2 back.
Cool.
Pretty interesting.
Yeah.
Yeah.
Pretty interesting. And if we can show that this pattern is true forever with these powers, since we know that would tell us for sure that we would always get into the integer, why does this pattern tell us that if I start with 2 2's, I'm always going to get integers from then on?
Well, because if you start with 2 2's, the first integer, there's no integer before it.
Well, right, I start with 2 2's, and that's how I get my 6.
Yeah.
So this one, I get 6 is 4 plus 2.
Because you're not dividing anything.
You're never dividing anything. Why else? Why can you give me an explanation for why this always produces integers?
Well,
If I start with integers, I always get integers.
there's no fractions or anything in the formula.
There's no fractions. I'm just, if this is an integer and that's an integer, that's an integer.
Yeah.
So if I can prove this formula, then I'm always going to get integers.
Yeah.
But I knew this got closer and closer to 0, right?
Yeah.
But when I add this thing that's closer and closer to 0 to this thing, I always get an integer. That means this thing
It's
must be
close.
really close to an integer.
It's closer and closer to an integer.
And James Tanton was asking, do I get 1,000,000 nines?
Sure seems like it.
At some point I will.
Yeah.
At some point I will. In fact, this formula is going to tell you even what power is the first time you're going to see 1,000,000 nines, which is pretty cool. You can solve that equation. Okay, now I mentioned I was going to relate this to the Fibonacci numbers.
Yeah.
Okay, let's do that. This is our last movie. This was actually what? D?
Yeah.
Okay, so the next one's gonna be E.